Hello everyone, welcome to Hunt Electronics. This is your friend Saqib, and today's technical topic is a logic gate using a transistor. So, in today's session, we are going to see how we can implement basic gates like AND gate, OR gate, NOR gate using a transistor BC547.
Okay, so let us see the first AND gate. So we know the AND gate. So this is two input AND gate. So where A and B is input and we get the output over here. So this is the truth table for AND gate. So we know the logic about the AND gate. When both the inputs are logic 1, then the output is 1. At the rest of the time the output is always 0. That's why it is said as that when A and B both are at a logic 1, then the output is 1. That's why it is known as a AND gate. Now let us implement this AND gate using the transistor. Here we have taken the two transistors Q1 and Q2. Here A and B are the input to the base of the transistor, and we are taking the output from the emitter side of the second transistor. So when A is logic 0 and B is the logic 0, there is no flow of charge from emitter to collector to emitter and again collector to emitter, so the output is always 0. When the A becomes the logic 1, there is a flow of charge from collector to emitter in this way. When B is also at a logic 1, then again there is a flow of charge from the collector to emitter, and hence the output becomes 1. Let us see this using the actual circuitry. Now you can see here, so there are two transistors are there, Q1 and Q2, and we are taking the output. So there are three LEDs are there. So LED A1A, LED B, and the output at the LED. So there are three LEDs are there. So this first white, this is input to the A1, then this is input to the B, and then the output is taken from here at the emitter side of LED. Now let us study about the first logic. The first logic says that when A is at logic 0, B is at the logic 0, the output will be also 0. So you can see here A LED is off state, B LED is also in the off state, so the output is also off. So hence the it is verified. Now A at logic 0 and B at logic 1, then the output will be on. So I'll just connect B at a logic 1. I can see here the A is logic 0, B is at the logic 1, and the output is also 0. So A is 0, B is 1, and output is also. Now we'll turn out at the A logic 1. I'll just connect to the plus. Now A is at the logic 1, B is 0, still the output is 0. So A at the logic 1, B is at the logic 0, and still the output is logic 0. Now in the next, A is at the logic 1. Okay, you can see that green LED. Then B is at the logic 1. So you can see the B, and the output is also 1. So A at logic 1, B is also 1, and output is at 1. Okay, so hence we can see that when both the inputs of the AND gates are at a logic 1, then the output is also a 1. Hence we have proved the AND gate. Now the next is OR gate. So for the OR gate, when A or B, if anyone is at a logic 1, then the output is 1. So we can see that. So for 0 0 output is 0, 0 1 the output is 1, 1 0 the output is 1, and for 1 1 the output is 1. So here also I have taken the two transistor, that is BC547. The collector of the first transistor is connected to the collector of the second transistor. The emitter of the first transistor is connected to the emitter of the second transistor. So the output is taken from across a second transistor, that is through the LED. Here A and B are the input to the base of the transistor. Now let us see with the actual circuitry. So here you can see the OR gate over here. So there are two transistors over here. A and B is the input, O is the output. So this green color wire, it is the input to the first transistor, then second transistor. Now let us see whether it can satisfy the truth table. So where now we can see the A is at the logic 0, B is at the logic 0, so the output is also 0. When A is at the logic 0, okay, B is at the logic 1, the output is 1. So this is B, let us connect it to the logic 1, and okay, now you can see A is logic 0, B is logic 1, the output is also logic 1. Okay, so the next point, so A is at the logic 1, B is logic 0, hence the output is also 1. So here A is logic 1, B is logic 0, and the output is also at a logic 1. So it satisfies this. Now, when A is at the logic 1, B is at the logic 1, the output is 1. So here the A is at the logic 1, B is also at the logic 1, hence the output is also 1. So for the OR gate, so if any one input of the OR gate is at the logic 1, then the output is always 1. Okay, next is NOT gate. So NOT gate is nothing but the output is the complement of an A, of an input, sorry, that is A. So if you can see in the truth table, the first, when the A is 0, at the logic 0, A complement is 1. When A is at a logic 1, the A complement it as a logic 0. So the output is always complement of the input. Okay, now let us see. So to achieve this, we have used only a single transistor over here, that is BC547. Here the A complement is the output and A is the input to the transistor. So the input is given to the base of the transistor over there. So when A is at the logic 1, okay, the transistor, whatever the current over from the collector, it starts flowing towards the emitter. Hence there is no current at the output, so the output is at the logic 0. When the base of the transistor, that is input, is at the logic 0, the transistor is in totally off state, so there is no flow of charge from collector to emitter. Whatever the charge over there from the VCC to the collector, it will go to the output, and hence the output will be at the logic 1. So let us see with respect to the circuitry. So here I've got a NOT gate using BC547 over here. So here A is the input and A complement is the output. Now you can see the input, that is A, at the logic 0, and you are getting the output. Now I'll change the input from the logic 0 to 1. Now see, the input A is at the logic 1, so the output becomes the logic 0. If I change the state again, now the input, that is A, is at the logic 0, so output 1. So for the NOT gate, always the output is the complement of the input.